Bottom. Okay, good morning everyone, and welcome to lecture 20 of 124103 biophysical principles. In this lecture we will talk about waves. So this is the second lecture in the last topic that we'll cover in this course. Last time we started this topic by talking about periodic motion, the oscillation of an object, looking at a particular kind of periodic motion called simple harmonic motion. And we've identified what amplitude, period, and frequency is. Now, in this lecture, we'll see what happens. So when an object oscillates, it sort of disturbs its surroundings. And in this lecture, we'll see what happens when this disturbance propagates. We have what we call a wave. So we will, in this lecture, define what a wave is. And then we'll differentiate between the two main types of waves and give examples of each. Like we did in periodic motion, where we identified the amplitude, period, and frequency from the sinusoidal graph. We will also do the same for the wave. We will identify the amplitude, frequency, and what we call wavelength of the wave. And of course, we'll define what the wavelength is, and then we'll define what speed of the wave is. We'll also look at some phenomena that happens when waves interfere with another wave. For example, we have what we call interference, and we'll look at two kinds of interference. And then we'll look at what happens when the wave encounters an obstacle or an opening, looking at diffraction. Okay. All right, so let's define what a wave is. Formally, the wave is defined as a traveling disturbance that propagates from one point to the next, and as the wave travels, it carries with it energy, but it does not transfer matter. In short, you have this oscillating disturbance. You have this oscillating object, and you have this disturbance that propagates through space, but the actual oscillating object does not propagate itself. And you can think of a stadium wave or a Mexican wave as an analogy of this. So here you can see in this picture a stadium. Maybe at one point, people decided to do this wave, Mexican wave, and notice how that sort of travels around the stadium. Okay, so it's the wave, the disturbance, the waving action that travels around the stadium, but the people stay in their seats, right? So the people don't travel themselves, but it's just the waving motion or action that travels around the stadium. So that's sort of how that's a good analogy of what's happening in waves. Yeah, so relating, as I've mentioned earlier, the wave is related to the simple harmonic motion that we've talked about in the last lecture. So we've seen last time, you have, for example, a mass that's connected to a spring, and this mass is oscillating up and down. We can represent the motion of this object using the sinusoidal graph. Okay, and we've defined the amplitude is the maximum displacement from the equilibrium of this oscillating object. And we define the period as the time it takes for one oscillation. And in the sinusoidal graph, it's the distance between two successive points in the graph. So because we're measuring period as the time it takes for one oscillation, notice how the x-axis of the sinusoidal graph that describes the periodic motion is given in time, which is measured in seconds, right? So in the simple harmonic motion, graph, sinusoidal graph, the x-axis is given in time, and therefore we measure the period as the distance between two successive points in the units of time, which is seconds. For the wave, okay, because the disturbance propagates through space, notice how the x-axis, so we can also represent the propagation as a sinusoidal graph shown here, but notice how the x-axis of the sinusoidal graph is given in distance, which is measured in meters as the SI or base unit. So if you compare the sinusoidal graph of the wave and the periodic motion, they're both sinusoidal. They both have an amplitude, and you can measure two successive points, the separation of two successive points. The main difference is that in the periodic motion, you measure the x-axis in time, whereas for the wave, you measure the x-axis in distance, right? Okay, so the wave will also have an amplitude, okay, and we can measure two successive points, the separation between two successive points, and we call that the wavelength. So let's look in more detail. Let's look at the details of these crests and troughs and amplitudes and wavelengths of the wave. So in the sinusoidal graph that describes the wave, you have the crest and the troughs as the locations of the maximum displacement from equilibrium position of the oscillating particle. Okay, so you can draw sort of here to remind yourselves, there's a particle that's oscillating, and it will have a maximum displacement, which we defined as the amplitude. So the propagation of the disturbance will also have an amplitude, which is the distance between the equilibrium and the crest or the trough. So the crest, that's the peak, the maximum positions along your sinusoidal graph. And the amplitude is measured between the equilibrium position and the crest, or the equilibrium position and the trough. It should give you the same measurement, just like we saw in the sinusoidal graph of a periodic motion. You can measure the amplitude from the equilibrium position to the positive maxima or the negative maxima. It will still give you the amplitude. Now, the distance between two successive points in your graph is what we call the wavelength. Instead of the period, we now call it the wavelength, and we represent wavelength using this Greek symbol called lambda. Okay, so you read this Greek symbol as lambda, and because wavelength is the distance between two successive crests or two successive troughs, and the x-axis is measured in meters or the distance. Therefore, the unit for the wavelength will also be the unit of distance, which is meters for the SI or base unit. Right? Okay, so essentially it's similar to the periodic motion. You have the amplitude, which gives you the maximum displacement of the oscillating particle. The only difference is that the distance between two successive points is now the wavelength lambda, and that is measured in meters. Okay. Now, as the wave propagates, we can also define the speed of the wave, the speed, how fast the disturbance travels. And the speed is given by this equation. It's related to the frequency and the wavelength. Frequency F in this equation is the frequency. That will be the frequency of oscillation of the particle that's undergoing simple harmonic motion. And wavelength is the wavelength of the traveling disturbance, the distance between two successive points in the sinusoidal graph of the traveling disturbance that we've seen in the previous slide. So, yeah, so wavelength and frequency. So speed sort of relates the frequency of the oscillating particle with the wavelength of the traveling disturbance. If we analyze the speed of the wave, this equation actually came from the basic definition of speed. So we've learned in the very first lecture that speed is equal to distance divided by time, right? So frequency, we've learned last time, it's related to the period. So we can also write the speed as equal to the wavelength divided by the period, recalling that frequency is the inverse of the period. Okay, so if we look at the definition of speed being distance over time, the distance would be how far the wave has propagated over a particular time. In this case, the time will be one period, and the distance will be the wavelength of the wave. So you can think of the speed as being in one period of oscillation, the disturbance would have propagated through a wavelength, through one wavelength. Yeah, so if you can imagine the oscillating object, by the time this oscillating object finished one period, one oscillation, the disturbance would have traveled a distance of one wavelength. Okay, and so speed is equal to the wavelength, the distance traveled, divided by the period, which is the time for one oscillation of the particle. And period is equal to the inverse of a frequency of the frequency, and therefore speed is equal to wavelength times the frequency. Right? Okay, so just to summarize the wave will have the wavelength, it will have the amplitude, and then speed. Speed is related to the wavelength and the frequency of oscillation of the particle. Right, just before we continue talking about waves and looking at the classifications of waves, let's just look at an example of the speed of a wave. So here we have a killer whale. Echolocation is a form of sensory perception used by killer whales to detect obstacles. And here you have a whale that emits a pulse of sound, which reflects from an object, and the reflection is detected by the whale. And from there, it sort of is able to know how far the obstacle or the object is. So for this particular example, echolocation waves are emitted by a whale at a frequency of about 200 kilohertz. And the speed of the whale's echolocation wave in seawater is 1.39 times 10 to the 3 meters per second. And we are being asked, what's the wavelength of the echolocation wave? And if a school of fish is 10 meters in front of the whale, how long after the whale emits the wave is its reflection detected? Okay, all right. So for any given problem, we'll use the same strategy that we've always been using. It will be useful to pick out the given information that we can use to solve the and to answer the questions. So we're given the frequency of the wave, 200 kilohertz. Okay, the unit for frequency is hertz. So having this prefix kilo means that you have kilo is 10 to the 3. So that means the frequency is equal to 200 times 10 to the 3 hertz. Right, so be very conscious of those prefixes. You'll often see them in waves, especially the wavelength can be very small in nanometers. So yeah, just be conscious of those prefixes and make sure that you convert them to the correct equivalent number. Okay, so 200 kilohertz means 200 times 10 to the 3 hertz. We're also given the speeds, 1.39 times 10 to the 3 meters per second. We know that the speed is related to the frequency and the wavelength. Okay? Speed is equal to wavelength times frequency. We're being asked for the wavelength, so we need to rearrange this equation to isolate lambda, the wavelength. Okay, if we divide both sides by f, then we're able to cancel frequency on the right side because frequency divided by frequency is equal to 1. And you essentially have wavelength is equal to speed divided by the frequency. Speed that's given 1.39 times 10 to the 3, and the frequency is also given 200 times 10 to the 3. And you have the wavelength 6.95 times 10 to the minus 3 meters. Right, a very common, so in just in terms of prefixes, a common unit for wavelength, especially for light, is the nanometer. Common unit for the wavelength is the nanometer. In nano, so it will be worth remembering that the prefix nano is times 10 to the minus 9. So if you're given the wavelength in nanometers, make sure to change nano to times 10 to the minus 9 to convert that nanometers to meters. Okay, are we happy with the solution for the wavelength of the wave? Good, all right. Okay, second question, you have fish, the fish that's 10 meters. So you have a school of fish 10 meters away from the whale. The whale gives off this echolocation wave 10 meters away. How long after the whale emits a wave is its reflection detected? So you have this wave going to the school of fish and then reflected backwards. Okay. So how long means we're being asked for the time. And we know speed is equal to distance over time. So we're given 10 meters is distance and we're given time. So we want we're being asked for the time, how long. So we want to solve for time, right? Rearranging speed is equal to distance over time. We have time is equal to distance divided by speed. Right? What distance should we use here to find the time? Yeah, good, right? So it's a reflection. The wave is reflected. So you have 10 meters going towards the school of fish, and you have the reflection traveling another 10 meters. So we assume that we can model the school of fish and the whale as point sources. So you have their equal distances for the wave and its reflection. Okay, so the distance should be 20 meters, and you have the speed, which is given in the information. You have a time of 0.014 seconds. Cool. Are we happy with the solution to this question? Good. So the key equation so far we've seen is speed equals wavelength times frequency. But of course, you can also use speed equals distance over time depending on what's being asked in the problem. So don't forget about the previous concepts that we've learned. They would still be applicable throughout the course, like basic concepts like speed equals distance over time, acceleration equals change in velocity over time, and so on. Okay, right. So depending on, so we've seen, oscillating objects undergoing simple harmonic motion, and it generates a disturbance. The disturbance propagates. The propagation of the disturbance is what we call the wave. We can classify the wave depending on the relative direction of the propagation with respect to the direction of oscillation of the particle. We can classify the wave as a transverse wave or a longitudinal wave. Sorry. So here you can see some examples of transverse waves is light or a wave on a string. Longitudinal waves, an example of that will be sound. And next week we'll be focusing on sound. Right, but first let's distinguish, compare and contrast between transverse and longitudinal waves. So for transverse waves, the direction of propagation of the wave is perpendicular to the direction of oscillation of the particles. Okay. Whereas for the longitudinal wave, the direction of propagation of the wave is parallel to the direction of oscillation of the particles. So that's the main difference between the transverse and longitudinal waves. For transverse waves, they don't need a medium in order to propagate. And that's why light being a transverse wave can propagate through space. Okay. So electromagnetic waves that we've seen when we talked about heat last week, they're an example of a transverse wave, and that's why they can propagate through space, through vacuum. Longitudinal waves, on the other hand, they need a medium in order for them to propagate. So without a medium, you will not be able to hear sound. Okay. And in the next slides, we will see why longitudinal waves will need a medium to propagate through. But yeah, let's look at each of the kinds of waves in more detail. So for the transverse wave, so here's an animation showing a transverse wave. You have here, you're disturbing the particles by oscillating them up and down. You have this up and down motion, and you have the disturbance, the wave that's propagating to the right. So notice, so the red dots here in the animation represent the oscillating particles. So notice how the particles are just oscillating up and down. And they're stationary where they are, meaning they're not traveling to the right. So the particles are just staying put, but they're just moving up and down. They're oscillating up and down, while the wave, the disturbance, is propagating to the right. And notice how the propagation to the rightward propagation of the wave is perpendicular to the up and down oscillation of the particles. So that's the transverse wave. Okay, we can model a transverse wave using a slinky. So here's a demonstration of a transverse wave using a slinky. So this video doesn't have sound, so that's fine if you don't hear anything. It's just a demonstration of, see, all right. So you have the slinky being displaced on one end. It's being disturbed up and down. So yeah, you're shaking the slinky up and down, and you have the wave propagating to the left. Right. So for a transverse wave, it's easy to see. You can visualize the sinusoidal nature of the wave of the propagating disturbance. Yeah, so for a transverse wave, it's easy to visualize the sinusoidal nature of the wave. You have here, you can represent this as the crest and the trough. Right, and the displacement relative to the equilibrium position, that's the amplitude, and the wavelength is the distance between two crests and two troughs. Right. So that will be the wavelength for the wave. Right. So if, yeah, so for this demonstration with the slinky, it's easy to visualize the sinusoidal motion of the wave, and you can easily identify the crest and the trough and the amplitude and the wavelength. Okay, for the longitudinal wave, the oscillation of the particles are parallel to the direction of propagation of the wave. So this animation shows an air column. Okay, so you have the black dots there are air molecules. And you have a plunger on one end, okay, and the plunger is being moved to and fro. That disturbs the air molecules in the column, and you have the disturbance propagating through the air column to the right. So notice how so again, the red dots here represent the particles that are oscillating in the air column. So notice how the red dots, the particles are just oscillating to and fro. They, in a way, they're not moving large distances. They're staying put. They're just oscillating about their equilibrium position, okay? And they're oscillating to and fro, whereas the wave, the disturbance, is propagating to the right. And notice how the direction of propagation of the wave is parallel to the direction of oscillation of the particles. Okay. Yeah. And the wave propagates through the compression and rarefaction of the particles. Yeah, we can represent the longitudinal wave using the sinusoidal graph as well, but I guess a demonstration would make it more easier to relate the longitudinal wave and the sinusoidal graph. So watch this demonstration using a slinky. Let me just share my computer sound. Okay. So when you hear the sound of, you should hear a sound.
Okay, in this demonstration, we're going to look at longitudinal waves. Most of the diagrams of waves you've seen so far have probably been transverse. This is the classic sine wave that gets drawn on the chalkboard up and down and back. And that's a useful diagram, but it doesn't illustrate very well how sound propagates through the air. Sound propagates through the air as what's called a longitudinal wave. So sound is not going up and down. Sound is propagating through the air through air molecules that, if you can imagine all the molecules in the air here, running into each other. So those molecules get compressed and then rarefacted, and then compressed and then rarefacted. The molecules themselves do not travel through the air. They stay where they are. They just bounce off the thing next to them, and that one bounces off another one and bounces off another one. What we have here to demonstrate this is essentially a slinky suspended in a cage. And if you could imagine each little wire of the slinky representing an air molecule, what I'm going to do is start vibrating one end of the slinky, and you can see that the one wire bounces off another, that bounces off another, and ultimately propagates that energy down the length of the spring. This is what's called a longitudinal wave. And this is a much closer example of how sound propagates through the air. Keep in mind, though, that sound propagates equally in all directions. So sound is not a running column going through the air. This is happening in a 360-degree sphere. But if you can keep in mind that this is how the sound actually propagates through the air, it will help you as you end up staring at all of these diagrams of sine waves that are inevitable, even through the material that we will show you. Keep in mind that sound is not going up and down. It's actually traveling longitudinally like this, and that'll help you keep straight the physics involved in sound and wave propagation in the air.
Right. Okay, so that's a good demonstration of a longitudinal wave. And if you've noticed in the slinky, there are sections of compression and rarefaction, where the slinky is compressed and slinky is sort of stretched out. So the compressions, the regions of compression, they are, if you relate that to the air molecules for which sound is propagating through, so those regions of compression are regions of high density. So it's these darker regions here, regions of high density and also regions of high pressure. So those regions of compression, high density and high pressure, they correspond to the crest of the wave. If you draw the sinusoidal, if you draw the wave as the sinusoidal graph, the regions of compression will correspond to the crest, and the regions of rarefaction, where the slinky is sort of stretched out, the regions of rarefaction correspond to the regions of lower density, okay, in the air column, for example. So R means rarefaction, C means regions of compression. And those regions of rarefaction correspond to lower density and also lower pressure in the medium. And those regions of lower density, lower pressure, and rarefaction, they correspond to the trough of the sinusoidal graph for the wave. So you can sort of draw the sinusoidal graph representing the longitudinal wave. And you can see that the wavelength, which is the distance between two successive crests or two successive troughs, can be obtained as the distance between two successive crests. For example, that's one wavelength, or the distance between two successive troughs, two successive rarefactions, that will give you the wavelength for the longitudinal wave. Right. Okay, are we happy with the distinguishing between the two kinds of waves, transverse waves and longitudinal waves? Yeah, good. Also knowing, identifying the wavelength and the amplitudes for the longitudinal and transverse waves would also be an important concept to grasp. Okay, so if we're happy with transverse and longitudinal waves, and let's now look at some phenomena that can occur when a wave meets another wave, that will be interference, and when a wave meets an obstacle or an opening, that will be diffraction. But first, let's talk about interference. Okay, so consider two pulses. So a pulse is just one peak. Consider two pulses that are traveling in opposite directions as shown in this animation here. Notice as the pulses meet, when the pulses overlap, they sort of reinforce each other. So there's this adding up of the amplitudes of the pulses according to the principle of superposition. So the principle of superposition simply says that when these two pulses meet, their amplitudes add up. Now, if the two pulses meet such that their crests overlap, then their amplitudes will add up constructively, and that results, to a higher amplitude, a bigger amplitude, and we call that constructive superposition. Okay, it's the same way when two troughs superimpose. So when two pulses meet such that their troughs coincide with each other, we also have this reinforcement of the amplitudes. So you have constructive superposition as well. Okay. But when the crest coincides with the trough, you have this canceling out. You can think of it as a positive amplitude adding up with a negative amplitude, and you have this cancellation of the amplitudes, and we call that destructive superposition. Okay, right now with waves, we can have the superposition of overlap or overlapping of the two waves, which we call interference. It's the same concept when the two waves are in phase. So as you can see in this diagram here, that the top two waves, they are what we call in phase, meaning their crests coincide with each other and their troughs coincide with each other as well. So when they overlap, you have this reinforcing of their amplitudes, and we call this constructive interference. You have this resulting amplification of the amplitude. On the other hand, if the two waves are what we call 100 degrees out of phase, as we see in this illustration, it's these two bottom waves here. Notice how the trough of one wave coincides with the crest of a second wave. Okay, so we say that they are 80 degrees out of phase, and when they superimpose, that results to the cancellation of the amplitudes. So we have here the crest coinciding with the trough, resulting to the cancellation of the amplitude. So we call this destructive interference. Right. So we can demonstrate constructive and destructive interference using, for example, a ripple tank. So watch this video demonstrating constructive and destructive interference.
In this video, we will demonstrate constructive and destructive interference of water waves using a Pasco ripple tank. The ripple tank setup is shown here. On the left is a motor that oscillates with different frequencies and amplitudes. Above a thin layer of water is a light source, and below is a mirror that reflects the ripples onto a screen. This video was recorded using a high-speed camera so that 1 second in real time is represented by 15 seconds in this video. Here, plane waves are incident upon two openings. When a plane wave passes between two openings, the result is like creating two new waves. These waves can add together to form new waves, which is called superposition. When the two waves are out of phase with one another, they add together to create no wave. This is called destructive interference. These red lines show where destructive interference is happening. When the two waves are in phase, they add together to form an even larger wave whose amplitude is the sum of the amplitudes of the two waves. This is called constructive interference. These green lines show where constructive interference is happening. You can think about how this experiment might prove that light and sound are waves.
Okay, yeah, so let me just pause the video and point out, emphasize some points here. Yeah, it's a good demonstration. You can clearly see constructive and destructive interference. So the light lines here, they represent the crests of the wave, and the darker sections, that darker line here represents the trough of the wave. So notice, for example, at this point, that's the crest, the crest of this wave superimposing with the crest of this other wave. And notice how this is a very bright spot, which results from the addition of the amplitudes of those two waves. Okay, so you have this resulting bright spot, meaning you have here a higher amplitude compared to the individual wave. But notice at this point, for example, it's a dark section, and if you, so you have there the trough interfering with the trough. Okay, that means you have also a reinforcement of the amplitude, but it's like it's both, they're both negative. But here you have the crests. Yeah, the crest of this wave, the crest of that wave interfering with the trough of that wave gives you this darker point compared to this bright point here. So that's constructive interference, and this one shows you the destructive interference. Okay. Right. Cool. So that's the concept behind interference. Now, if two waves interfere with each other, meaning if two waves superimpose, or you have interference between two waves, they can form what we call standing waves. Okay? For standing waves to be formed, these conditions need to be met. So the waves should have the same amplitude, same frequency, wavelength, and they should be traveling in opposite directions. So a good way of achieving this will be a wave, an incident wave interfering with its reflection. So in this animation, you can see this wave propagating to the right. Okay, it gets reflected from this end, and this darker wave is its reflection. When they interfere, when they superimpose, they can form this standing wave represented by this blue wave here, and it's called the standing wave because, you know, if you can see here, it's sort of like the wave doesn't appear to be propagating. It just appears to be oscillating. It's stationary in space. Okay, but it actually consists of two waves that are propagating, but this resulting standing wave just appears to be stationary in space. Notice also that there are points in the standing wave where the amplitude is 0. Okay, and this is a point of destructive interference. So that point where the amplitude is 0 is called the node. And as you notice here, the node, that point remains still at all times with 0 amplitude. And you'll also notice a point in the standing wave where the amplitude is maximum. Okay, so you have there what we call an antinode. That's a point of constructive interference, okay, between the two waves. A good demonstration for creating standing waves would be vibrating a string whose one end is fixed. Okay, and this video demonstrates the generation of standing waves. So watch this video.
Standing waves are a result of reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode. Sending the pulse at twice the frequency results in the second harmonic. If I triple the frequency, I get the third harmonic.
Okay, so you see how how the standing wave appears to be. It's called standing waves because it doesn't appear to propagate through space. So it's just like the rope is just oscillating up and down, but it actually consists of a wave and its reflection that's propagating. So the video mentioned something about harmonics and second harmonic and fundamental frequency. So in the workshop, we'll look more closely into that frequencies, fundamental, second harmonic, and so on, standing wave frequencies, because it's easier to understand those harmonics by doing a simulation yourself. So there will be a PhET simulation in the workshop, and then we'll from that simulation we'll formulate relationships between the frequencies of standing waves, right? But for this lecture, at least understanding the concept behind what a standing wave is, how is a standing wave generated, identifying the nodes and antinodes in the standing waves would be the crucial information from the lecture, right? Okay, so with that, are we happy with the concepts of standing waves? Okay, yeah, so standing waves, that's the interference between a wave and its reflection. When waves interfere in time, they can also form an interference pattern called the beat. Oh, okay. Right. So beats. So a beat is also a result of interference of two waves, but for a beat to be formed, the waves need to have same amplitude. They should be traveling with the same speed in the same direction, but they should have slightly different frequencies. So these are the conditions for forming beats. So here you have this figure shows you two waves, the blue wave and the pink wave. They have the same amplitude. So notice how, right? Their amplitudes are the same, but they have slightly different frequencies. So the pink wave here has 50 hertz frequency and the blue wave 60 hertz frequency. And we know that they have different frequencies because they're slightly out of sync. They don't completely overlap. So they're slightly out of sync. That means they have slightly different periods. Okay? Frequency is the inverse of the period, and period is the distance between two successive points along your wave, along the oscillation of the periodic motion. So they have slightly different frequencies. It's sort of like the formation of beats is sort of like two drums that are beating out of sync. And unfortunately, the website where I get this animation disappeared and Flash is no longer working. But luckily, I was able to record some video showing, illustrating these. So the two waves with slightly different frequencies, it's like two drums that are beating out of sync. So have a look. It is like these two drums that are playing out of sync. Initially, they start out playing out of sync, but after some time, they play in sync before playing out of sync again. Yeah, and they're in sync at this point. And then they become out of sync again. Right? So if we it is like, so if we represent the beating of these two drums as the sinusoidal waves here, so you have they're starting out of sync. Okay, and they're out of sync. At some point, they are completely out of sync. Okay, and then at one point, they are completely in sync. So you have there the crest corresponding, the crest of one wave corresponding to the crest of another wave, and then they become out of sync again. And so if we do the superposition and look at the interference of these two waves, okay, at the point where they're completely out of sync, notice how the crest of one wave corresponds to the trough of the other wave, so they're completely out of sync, they're out of phase, and the resulting amplitude will be 0. And when they're completely in sync, you have the reinforcement of the amplitude. So the amplitudes add up and you have this maximum amplitude. And in between, where they're out of sync, you have this varying amplitude. And so your amplitude goes from 0, where they're completely out of sync, to some maximum amplitude where they're completely in sync. And then they become out of sync again until they're completely in sync at that, out of sync at this point. So you can, if you notice, you can sort of draw like an envelope wave, like such. Okay, and if we zoom out so that we are able to see more crests and troughs, if we zoom out this section here, we can see something like this. Okay, so you have here the first wave at a certain frequency F1, the second wave with a slightly different frequency F2. Okay, the superposition of these two waves forms this beat wave. You have there completely out of phase or out of sync, 0 amplitude. And here completely, right here, at this point, they're completely in phase. And so you have this maximum amplitude. And you have these wave, this envelope wave, which we call the beat. And from this envelope wave, we can also measure the distance between two successive points. Okay. And determine what we call beat frequency. Okay. So the beat frequency can be determined by subtracting the frequencies of the two waves that form the beat wave. Okay. You can see there's a bar here. So these two bars here means absolute value. Absolute value means that the answer F1 minus F2 should always be positive, which means that it really doesn't matter whether you get a positive or a negative number. Let's say F1 is equal to 8 Hertz and F2 is equal to 10 Hertz. So F1 minus F2 will be equal to negative 2 Hertz. The absolute value symbol means that you should just disregard the negative, and the beat frequency will be equal to positive 2 Hertz. Okay. Okay, a practical example of the beat frequency can be demonstrated here, right? So for you to form beats, you should have two waves with slightly different frequencies. So let's say you have a wave whose frequency is 440 Hertz and another wave whose frequency is 442 Hertz. In the next lecture, we will learn, when we learn about sound, you will learn that the frequency of a wave is related to the pitch of sound. So here you have, we'll use sound to demonstrate beats. So you have sound whose frequency is 440 Hertz, and we have another sound which has a slightly different pitch because it has a slightly different frequency, which is 442 Hertz. And we'll see what happens when these two sound waves interfere with each other. So listen to this video.
Here we have two waves with slightly different frequencies. One with 440 Hertz and another one with 442 Hertz. This is how a 440 Hertz sounds like. And this is how a 442 Hertz sound like.
So let me just stop there. So listening to that 440 Hertz and 442 Hertz, are you able to distinguish the difference between them? I mean, can you distinguish the difference in the pitch of 440 Hertz and 442 Hertz? No, yeah. Some people who has perfect pitch, they can. And I have a friend who is, and she says it's annoying as she plays a musical instrument. But some people can, but ordinarily we cannot, right? I cannot distinguish between the two sounds. Now listen, let's continue the video.
Here we have two waves with slightly different frequencies. One with 440 Hertz and another one with 442 Hertz. This is how a 440 Hertz sounds like. And this is how a 442 Hertz sound like. If we add these two together so that they interfere or superimpose, this is how the addition of 440 plus 442 Hertz sound like.
Yeah. So can you hear that wing, 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 that modulation of the sound? Okay. I'm not sure. So were you able to hear that? Yeah, good. Yeah, so that wing, wing, that's the beat that is formed. So you can sort of say that's So it's like this, yeah. You can, if you trace out the corresponding sinusoidal graph for that beat that is formed, you have this modulation in the sound. So the formation of beats, especially with sound, is usually it's used to tune musical instruments. So what musicians do is they have a reference frequency, which they want the pitch of their instrument to be at. And when they string, for example, a guitar, they string the guitar. If the frequency of sound from the guitar is different from the perfect pitch, the reference frequency, they will hear that beat, that they will see this beat from from their gadget, from their instrument, and so they tune their guitar until that sound disappears, or they tune their guitar until they don't see this beat wave anymore. Then they can say that their guitar is perfectly tuned because the frequency of the wave coming from their guitar matches the frequency of the perfect pitch, which they used as the reference. So that's the concept behind beats. It's slightly two different frequencies, being waves with two slightly different frequencies interfering in time.
Here,
The last concept with phenomena with waves is diffraction, and we can observe diffraction when a wave encounters an obstacle, as shown here. You have let's say water waves encountering a barrier or an obstacle. Notice how the waves bend around this obstacle, and so you have the shadow region where there is no wave there. We've also seen in the video of interference of water waves, okay, when you have a wave and it encounters an opening, you've seen in that video that the wave also bends around this opening, and so it forms like these bent waves. So a plane wave, straight waves, they're encountering an opening, will bend around the opening. A wave encountering an obstacle will bend around the obstacle, and you have this shadow region. So it's quite different. The phenomenon is quite different when between an obstacle and an opening. When the wave encounters an obstacle, you have a shadow region behind the obstacle. When the wave encounters an opening, you have waves outside the opening, but the waves are bent around the opening. So that phenomenon of bending of the wave is called diffraction. Okay? And yeah, this video, this is the last video we'll watch. It demonstrates, probably illustrates diffraction.
You may have noticed this before. Someone is talking in a room over here, and someone else is listening in a room over here.
You'll notice that voices sound kind of muffled through the wall.
But if we open the window, my voice is clear as day. So how does sound exit one window, make a 180-degree bend, and come in through this window? That is the fascinating world of diffraction. What happens when sound hits a window? Or more generally, what happens when a wave hits some sort of opening? Let's imagine a simple wave approaching a small gap in a wall just ahead. That's one fashionable wave. Because there's a gap, some of the wave can get through. But what does it look like on the other side? Does the wave continue in a straight line? Well, since there's nothing containing the wave on the other side of the gap, the wave expands in all directions. The wave looks as if it's radiating out from a single point. This is an example of Huygens principle. That is, when a wave is disturbed, each point where there is a disturbance becomes the source of a spherical wave. A disturbance is simply whenever something's in the way. So when there's a small gap, that gap becomes a source for a spherical wave. For a large gap, every point along the gap becomes a source for a spherical wave. In either case, this is known as diffraction. A wave does crazy things because it ran into something. You can even try this at home. Just get a baking sheet and fill it with some water, as such. Take a piece of cardboard, fold it in half, and tape the ends together. Then with two little walls, we can just stick them in our vat of water here, creating a little gap in between the two. And if you create a wave on one side of it, no matter what you do on one side of the cardboard obstruction, you can see that you get little circles coming out of the other side. You'll notice also there's a part of the wave that moves along your obstruction. Jumping back to the window, there is a part of the wave that moves along the wall. So sound can easily go out one window, creep along the wall, and climb right back in the other one. A little creepy, but kind of cool.
Right. Okay, so that's kind of a cool way of thinking about diffraction. Yeah,
You may have
but that also ends our lecture on waves. So you've noticed that for this topic on waves, it's mostly really just conceptual understanding of what a wave is, what's a transverse and longitudinal wave, what's interference, constructive and destructive interference, what's a standing wave, what is diffraction, and what is a beat. The only really numerical problem solving that we will do with waves is relating to this equation V is equal to lambda f, or speed is equal to wavelength times frequency. And you will probably also be given, for example, a sinusoidal graph. And from there, you can pick out what's the wavelength of the wave. Okay, and from the wavelength, you can find the speed given the frequency of oscillation of the particle. Right, but that ends our lecture for today. In the workshop, so let me keep that, and